Out in the vast darkness of space, where entire galaxies swirl like dust in a cosmic wind, lies a place that defies everything we think we know. The Coma Cluster isn't just another group of galaxies, it's a puzzle box of the universe, packed with mysteries so strange even the brightest minds can't fully explain them. Picture this: galaxies that vanish without a trace, black holes behaving like they've broken the rules, and invisible forces twisting reality itself. These aren't just science fiction ideas, they're real, they're happening right now, and they're hiding in plain sight within this incredible cluster. Today, we're diving into 25 of the most mind-bending, head-scratching phenomena lurking in the Coma Cluster. Each one challenges our understanding of space, time, and the very fabric of reality. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. Now let's zoom in on our first cosmic conundrum, one that's left scientists scratching their heads. Imagine a galaxy, vast and spinning, but with a critical piece missing. Dark matter, the invisible glue that should hold galaxies together, simply isn't there. This isn't science fiction, it's happening right now in the Coma Cluster. Normally, dark matter makes up about 85% of a galaxy's mass. It's the hidden scaffolding that keeps stars from flying apart as galaxies rotate. But in certain galaxies within the Coma Cluster, that scaffolding appears to have vanished. Take galaxy NGC 4889, for example. Observations suggest it's rotating far slower than it should if dark matter were present. Without that extra mass, the stars on its outer edges should be flung into space, yet somehow they're staying put. So what's going on? One leading theory points to tidal stripping. The Coma Cluster is a chaotic, crowded place with galaxies constantly tugging at one another. Over time, these gravitational interactions could rip away a galaxy's dark matter halo, leaving only the visible stars behind. Think of it like a thief in the night, stealing the unseen but leaving the furniture untouched. But here's the catch: some of these galaxies show no signs of disruption, making tidal stripping an incomplete answer. Then there's the possibility of observational errors. Dark matter doesn't emit light, so we infer its presence by watching how stars and gas move. If our measurements are off, say, because of dust obscuring our view or miscalculations in velocity, we might wrongly conclude dark matter is missing. Yet repeated studies with advanced telescopes keep confirming the anomaly, making this explanation less likely. Perhaps the most radical idea challenges our understanding of gravity itself. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently on cosmic scales, eliminating the need for dark matter altogether. While controversial, it's gained traction as a way to explain these odd galaxies. But if MUND is correct, why do most other galaxies still fit the dark matter model? The implications are staggering. If dark matter can simply vanish, our entire framework for how galaxies form and evolve might need rewriting. Or worse, what if we've been wrong about dark matter all along? The Coma Cluster isn't just hiding answers, it's forcing us to ask better questions, and that's just the beginning. Now, let's venture into the realm of alternative theories where the rules of the cosmos might not be what we thought. While tidal stripping and observational errors offer some clues, they don't fully solve the puzzle of the missing dark matter. That's why scientists have begun exploring more unconventional ideas, some of which could upend our understanding of the universe itself. One of the most debated alternatives is modified Newtonian dynamics, or MUND. This theory suggests that gravity doesn't behave exactly as Newton or Einstein predicted when dealing with the vast scales of galaxies. Instead of relying on invisible dark matter to explain galactic rotation, MUND proposes that gravity strengthens slightly in weak force environments like the outskirts of galaxies. This tweak could explain why stars in galaxies like NGC 4889 don't fly away even without dark matter's pull. But MUND isn't without its critics. While it neatly accounts for certain oddities in galaxy rotation curves, it struggles to explain other phenomena where dark matter seems undeniably present, like the gravitational lensing effect seen in galaxy clusters. The Coma Cluster, for instance, bends light in ways that MND alone can't easily justify. Supporters argue that MND might need adjustments or additional elements, but skeptics see this as a patchwork solution. The debate is far from settled, and every new observation adds fuel to the fire. Then there's the tantalizing possibility of exotic dark matter particles. Most dark matter models assume it's made of WIMP, weakly interacting massive particles, but what if it's something even stranger? Some theorists propose actions, ultra-light particles that behave more like waves than discrete bits of matter. Others suggest dark photons, particles that could interact with dark matter in ways we haven't yet detected. These ideas are speculative, but they're gaining traction as experiments like the Action Dark Matter search narrow down the possibilities. What makes the Coma Cluster so fascinating is that it's a testing ground for these theories. Recent studies have spotted galaxies where conventional dark matter models fail, yet MND doesn't quite fit either. This has led to hybrid theories. Perhaps dark matter exists, but its properties are more complex than we imagined. Maybe it can heat up or be stripped away under certain conditions, leaving behind galaxies that defy expectations. The stakes couldn't be higher. If dark matter isn't what we think, or if gravity works differently on cosmic scales, entire chapters of astrophysics might need rewriting. The Coma Cluster isn't just a collection of galaxies, it's a cosmic courtroom where the laws of physics are on trial. And as telescopes grow more powerful, we're inching closer to a verdict. Moving beyond the mysteries of dark matter, let's turn our attention to another cosmic oddity: ultra-diffuse galaxies, or UDG. These ghostly giants are as vast as our Milky Way, but contain just a fraction of its stars, making them nearly translucent against the darkness of space. The Coma Cluster is home to dozens of these enigmatic structures, and their very existence defies everything we thought we knew about how galaxies survive in such a crowded, violent environment. Picture a galaxy as delicate as a soap bubble, yet sprawling hundreds of thousands of light years across. That's the paradox of UDGs. In a place like the Coma Cluster, where galaxies frequently collide and gravitational forces tear them apart, these fragile giants should have been ripped to shreds long ago. Yet here they are, stubbornly intact. How? The leading theory suggests they're cloaked in an unusually thick shroud of dark matter, acting like an invisible shield against the cluster's chaos. But even this explanation falls short. Some UDGs show barely any dark matter at all, leaving scientists scratching their heads. Then there's the puzzle of their origins. Most galaxies in dense clusters like Coma are elliptical, compact, and star-deprived after eons of collisions. But UDGs are different. Their sparse, sprawling structure suggests they formed in isolation, far from the cluster's turmoil, before somehow drifting inward without being torn apart. Recent simulations hint that their survival might depend on timing. Perhaps they arrived late, after the cluster's most violent mergers had already passed. Others propose they're failed galaxies, born with too little gas to ever light up with stars. But the plot thickens when we look at their star populations. Some UDGs in Coma host globular clusters, dense knots of ancient stars, at rates rivaling much brighter galaxies. This implies they once had enough mass to form these clusters, only to lose it mysteriously over time. Could supermassive black holes have blasted away their gas, or did the cluster's gravitational tide strip them bare, leaving behind these cosmic skeletons? The Coma Cluster's UDGs are more than just celestial curiosities. They're forcing us to rethink the rules of galaxy evolution. If such fragile structures can endure in one of the universe's most hostile environments, what else have we gotten wrong? Every new observation peels back another layer, revealing a universe far stranger and more wondrous than we ever imagined. Now, let's shift our gaze to another electrifying mystery, the colossal radio halo shrouding the Coma Cluster. Imagine a faint, invisible ocean of radio waves stretching millions of light years across the cluster, far broader than any single galaxy within it. This isn't just background noise, it's a cosmic beacon hinting at forces we're only beginning to understand. Radio halos like this one are rare, and the Coma Cluster's version is one of the most massive ever detected. Unlike the sharp, pinpoint signals from pulsars or active galaxies, this emission is diffuse, almost ghostly, bathing the entire cluster in a whisper of radio energy. What's powering it? The leading idea points to high-energy electrons spiraling at near-light speed through the cluster's magnetic fields. But here's the catch: those electrons shouldn't last long enough to create such a vast halo. They'd lose energy too quickly, fading away long before they could spread so far. So how does the halo persist? One theory suggests turbulence from galaxy collisions re-energizes the electrons like a cosmic recharge. When galaxies merge, they don't just smash stars together. They send shock waves through the cluster's gas, accelerating particles and amplifying magnetic fields. It's a messy, violent process, but it might explain the halo's longevity. There's just one problem. Not all galaxy clusters with frequent mergers have radio halos, and some quiet clusters do. The Coma Cluster's halo, then, might be a puzzle wrapped in an enigma. Then there's the dark matter angle. Some researchers speculate that if dark matter particles collide and annihilate, they could release energy fueling the halo. It's a tantalizing idea, but so far, there's no smoking gun linking the halo's glow to dark matter. Others propose that the halo is a fossil, an echo of past activity from the cluster's supermassive black holes, whose jets might have dumped energy into the surrounding space eons ago. What makes the Coma Cluster's halo especially intriguing is its uneven structure. It's not a smooth blanket of radio waves. It has patches and voids, as if something or someone is sculpting it from within. Could this be evidence of hidden magnetic fields twisting and braiding through the cluster? Or are we seeing the fingerprints of ancient cosmic events, long forgotten but still reverberating? Every new radio telescope, from upgraded arrays to space-based observatories, brings us closer to cracking this mystery. But for now, the halo remains a cosmic question mark, a reminder that even in the silence of space, there are whispers we're still learning to hear. Now, let's turn our attention to a cosmic heavyweight that defies expectations: NGC 4889, a colossal galaxy at the heart of the Coma Cluster. This behemoth isn't just one of the largest galaxies we've observed. It's home to a supermassive black hole that's playing an unexpected game of hide and seek. Normally, black holes of this scale, weighing in at around 21 billion times the mass of our Sun, are anything but quiet. They're voracious eaters, surrounded by swirling disks of superheated gas and blasting out jets of energy that can be seen across the universe. But NGC 4889's black hole is eerily still, almost as if it's taken a cosmic nap. Why is this so puzzling? Think of it like a sleeping giant. A black hole this massive should be feasting on the gas and stars around it, lighting up its galaxy with intense radiation. Instead, it's in what astronomers call a quiescent state, cool, calm, and strangely inactive. One theory suggests that it's simply run out of food. Over billions of years, it may have devoured most of the nearby matter, leaving it in a quiet, energy-conserving mode. But here's the twist: the galaxy around it isn't starved of gas. There's still plenty of material floating around, which makes its inactivity even more baffling. Another idea points to the black hole's past. What if it went through a period of extreme activity long ago, blasting away nearby gas with powerful jets, effectively cutting off its own food supply? We see hints of this in the galaxy's structure: vast, faint bubbles of gas that might be remnants of ancient outbursts. If true, this could explain why the black hole is so quiet now. It's like a volcano that erupted so violently it exhausted its own magma chamber. Then there's the role of the Coma Cluster itself. The cluster's dense environment might be stifling the black hole's appetite. Gas falling toward the center of NGC 4889 could be getting stripped away by the cluster's gravitational tides or heated up by interactions with neighboring galaxies, making it harder for the black hole to feed. It's a cosmic balancing act where the very forces that should fuel the black hole's activity might instead be starving it. What's truly fascinating is what this tells us about how black holes evolve. NGC 4889's silent giant challenges the assumption that bigger always means louder. It's a reminder that even the most massive objects in the universe can enter phases of unexpected calm, and that their behavior depends on a delicate interplay of history, environment, and sheer chance. As telescopes peer deeper into the heart of this galaxy, astronomers are piecing together its story, one that might rewrite our understanding of how supermassive black holes live, feed, and sometimes rest. Up next, we'll explore another enigma, the Coma Cluster's surprising overabundance of hot gas, and what it reveals about the invisible forces shaping this cosmic neighborhood. Now, let's shift our gaze to another cosmic puzzle lurking in the Coma Cluster, an unexpected surplus of scorching hot gas. This isn't just any gas, it's a seething, X-ray emitting plasma that fills the space between galaxies, and there's far more of it than scientists ever anticipated. Picture a pot of water boiling over, but on a scale so vast it could envelop thousands of galaxies. That's the kind of excess we're dealing with here. So why does this matter? Hot gas in galaxy clusters isn't just cosmic decoration. It's a key ingredient in understanding how these structures evolve. The Coma Cluster's gas glows brightly in X-rays because it's been heated to temperatures of tens of millions of degrees. According to our models, there should only be a certain amount of this gas based on the cluster's mass and gravity. But observations reveal a glaring discrepancy. The Coma Cluster is practically drowning in it. One leading explanation points to violent mergers. Galaxy clusters grow by colliding with one another, and when they do, it's like two giant whirlpools slamming together. These collisions can shock the gas, heating it to extreme temperatures and trapping it in the cluster's grip. The Coma Cluster, being one of the most massive clusters we know, has likely undergone multiple mergers over billions of years. Each one could have dumped more hot gas into the mix, like adding fuel to a fire. But there's another player in this mystery, active galactic nuclei, or AN. These are supermassive black holes at the centers of galaxies that launch jets of energy into their surroundings. In the Coma Cluster, AGN might be acting like cosmic blowtorches, pumping energy into the gas and preventing it from cooling down. Normally, gas should cool over time and sink toward the cluster's center, forming new stars. But if AGN keep reheating it, the gas stays hot and puffy, leading to the overabundance we see today. Then there's the dark matter factor. While dark matter itself doesn't emit X-rays, its gravity dictates how the hot gas is distributed. If the Coma Cluster's dark matter halo is more complex than we thought, perhaps clumpier or more extended, it could explain why the gas is so spread out and abundant. It's like a hidden hand reshaping the cluster's anatomy without us even seeing it. What's fascinating is how this ties back to the broader universe. The Coma Cluster's excess gas might be a signpost for processes happening in other clusters too. If we can unravel why this gas is here, we could shed light on how all galaxy clusters grow, evolve, and eventually stagnate. It's a reminder that even the emptiest-looking spaces in the cosmos are teeming with secrets that challenge our assumptions and push us to rethink the rules of astrophysics. Up next, we'll delve into a ghostly mystery, the strange, nearly invisible galaxies drifting through the Coma Cluster, and why their faint glow defies everything we know about star formation. Now, let's turn our attention to something even more elusive, the ghost galaxies of the Coma Cluster. These aren't your typical cosmic structures. Imagine a galaxy so faint, so delicate, that it barely registers against the black backdrop of space. These ghostly formations are almost transparent, like celestial specters drifting silently among their brighter neighbors. But don't let their subtle presence fool you. They hold clues to some of the universe's most perplexing mysteries. So, what exactly makes a galaxy a ghost? These ultra-faint systems are incredibly diffuse, meaning their stars are spread out over vast distances, with very little of the dense packing you'd find in a typical spiral or elliptical galaxy. To put it in perspective, if the Milky Way were a bustling city, a ghost galaxy would be a handful of streetlights scattered across an entire country. Their dim glow comes from old, aging stars with hardly any newborn stars to brighten the scene. This lack of star formation is one of their defining quirks. But why do these galaxies produce so few stars? The answer lies in their environment. The Coma Cluster is a crowded, chaotic place where galaxies jostle for space and resources. For a small, fragile galaxy, surviving here is like trying to keep a candle lit in a windstorm. The cluster's immense gravitational pull strips away the gas and dust, the raw materials needed for star formation, leaving these galaxies starved and stagnant. It's a process called ram pressure stripping, where the hot gas between galaxies acts like a cosmic broom, sweeping away anything too loosely held. Another factor is tidal stripping. As ghost galaxies orbit the cluster, the gravitational tug from larger neighbors yanks at their outer stars, stretching them into faint, wispy trails. Over time, this relentless pulling can completely dismantle a galaxy, leaving behind only a faint skeleton of its former self. Some researchers even speculate that many ghost galaxies might be the remnants of once normal galaxies, slowly being erased by the cluster's relentless forces. Detecting these phantoms is a challenge. Their faintness means they often hide in plain sight, overshadowed by brighter objects or lost in the glare of the cluster's X-ray emitting gas. Astronomers have to use specialized techniques like ultra-deep imaging or filtering out background light just to catch a glimpse, and even then, many likely remain undiscovered, lurking just beyond the edge of our observational limits. What's fascinating is what ghost galaxies tell us about galaxy evolution. Their existence suggests that the universe might be teeming with similar faint structures, ones we've overlooked because our telescopes weren't sensitive enough. They also raise questions about dark matter. Some ghost galaxies seem to have far less of it than expected, which contradicts our current models of how galaxies form. Are these anomalies, or are we missing a piece of the puzzle? The ghost galaxies of the Coma Cluster are more than just cosmic curiosities. They're windows into the delicate balance of creation and destruction in the universe. Next, we'll uncover another hidden marvel, the mysterious glow of intracluster light, a faint illumination that lingers between galaxies like cosmic afterglow. Shifting our gaze to another cosmic mystery, let's unravel the secrets of the Coma Cluster's intracluster light, a ghostly glow that lingers in the emptiness between galaxies. Unlike the stars bound to galaxies, these are orphan stars drifting alone in the darkness, casting a faint illumination that hints at the cluster's violent past. But what exactly is this eerie light, and what stories does it tell about the chaotic dance of galaxies in this crowded region of space? Picture this: when galaxies collide or brush past each other, their gravitational tug of war can rip stars loose, flinging them into the void. These stars, no longer tethered to any galaxy, become cosmic wanderers, emitting a collective glow so faint it's often drowned out by the brilliance of their former homes. This is intracluster light, a diffuse, almost ethereal radiance that fills the spaces where galaxies once clashed. Detecting it requires painstaking observations, filtering out the glare of brighter objects to reveal this subtle cosmic whisper. One of the biggest puzzles is its uneven distribution. Why does this light pool in some regions of the cluster while barely touching others? The answer likely lies in the cluster's turbulent history. Simulations suggest that when galaxies merge or interact, their stars are stripped away in streams like crumbs scattered along a path. Over time, these streams mix and spread, but not uniformly. Areas with more frequent collisions, like the cluster's crowded core, show brighter intracluster light, while quieter outskirts remain dim. It's a cosmic fingerprint of past violence, a record of the battles galaxies have endured. But there's debate over the primary culprit behind this stellar exile. Some argue it's tidal stripping, the relentless pull of larger galaxies wrenching stars away from smaller ones. Others point to galactic collisions where direct impacts scatter stars like shrapnel. There's evidence for both. For example, the Coma Cluster's central regions, where galaxies are packed tightly, show trails of intracluster light aligned with the paths of known galaxy mergers. Meanwhile, the fainter glow in outer regions might stem from slower, more gradual stripping as galaxies orbit the cluster's core. The stars themselves add another layer of intrigue. Most intracluster stars are old and metal-poor, suggesting they were torn from small, ancient galaxies long ago. But surprisingly, some patches contain younger, brighter stars, hinting at more recent disruptions. Could these be the remnants of spiral galaxies whose gas-rich disks were shredded in violent encounters? Or is there another process, like star formation in stripped gas clouds, at work? The mix of ages complicates the narrative, showing that intracluster light isn't just a relic, it's an evolving phenomenon. What's at stake here isn't just a curiosity about lost stars. Intracluster light helps us map the cluster's dark matter. Since these orphaned stars follow the cluster's gravitational field, their distribution traces the invisible scaffolding of dark matter that binds the Coma Cluster together. Oddly, the light doesn't always align with dark matter models, suggesting gaps in our understanding of how gravity operates on such vast scales. As we peer deeper, this faint glow becomes a powerful tool, one that reveals not just where galaxies have been, but where they're headed. Next, we'll dive into the high-speed drama of galaxies racing through the cluster at impossible velocities, defying the laws of gravity as we know them. Now, let's turn our attention to one of the most baffling spectacles in the Coma Cluster galaxies that seem to break the cosmic speed limit. Imagine a highway where most cars cruise at a steady pace, but a few are zipping past like they've stolen a rocket engine. That's what astronomers see here, galaxies hurtling through the cluster at velocities so high they defy our basic understanding of gravity's grip. These high-speed galaxies aren't just outliers, they're rebels. According to conventional models, the immense gravitational pull of the cluster's combined mass, especially its dark matter halo, should keep galaxies moving within a predictable range. But some are racing far faster than those calculations allow. Take, for instance, a galaxy like IC 3976, which streaks through the cluster at speeds approaching thousands of kilometers per second. How? One leading theory points to dark matter interactions. If dark matter isn't distributed as smoothly as we assume, if it clumps unevenly or forms invisible slingshots, it could fling galaxies into overdrive. Alternatively, the cluster's own chaotic history might hold the key. The Coma Cluster didn't form peacefully. It grew by cannibalizing smaller galaxy groups, and each merger injected turbulence into the system. Picture a billiard game where every collision sends balls careening in new directions. Galaxies caught in these ancient pile-ups could have been launched on high-speed trajectories, their motions amplified by the gravitational chaos. Supporting this, we see some high-velocity galaxies aligned with the paths of suspected past mergers, like cosmic breadcrumbs leading back to violent events. Yet there's a twist. Not all speed demons fit this narrative. A few are racing toward the cluster's center, not away, as if drawn by some unseen force. This has led to a radical idea. What if dark matter isn't just a passive scaffold but an active player? Some models suggest rare interactions between dark matter particles could transfer energy to visible galaxies, effectively giving them a gravitational kick. It's speculative, but if true, it would mean dark matter is more dynamic and stranger than we thought. The stakes here are sky high. If we can't explain these velocities, our models of how clusters evolve and how dark matter shapes them might need an overhaul. It's like discovering traffic laws that only apply some of the time. Up next, we'll hunt for even darker secrets, the unidentified X-ray sources lurking in the cluster with no galaxies to call home. Shifting our gaze to another cosmic enigma, let's examine the Coma Cluster's ghostly X-ray sources, bright, pinprick emissions with no visible galaxies or stars to explain them. These point-like mysteries flicker in X-ray telescopes like cosmic fireflies, yet when astronomers train optical instruments on the same spots, they find nothing. No glowing gas, no bustling star clusters, not even a faint smudge of a galaxy. So what's pumping out these high-energy signals? One compelling suspect is rogue black holes, supermassive ones that were ejected from their host galaxies during violent mergers. Picture a game of interstellar pinball. When two galaxies collide, their central black holes can merge, and the gravitational recoil might fling the resulting monster clear of its galactic home. These wanderers would lurk invisibly in the cluster's depths, but as they pull in surrounding gas, that material heats up and shines in X-rays. We've seen hints of such nomads elsewhere in the universe, but the Coma Cluster's density makes it a prime hunting ground. Then there's the neutron star possibility. These ultra-dense stellar corpses, barely the size of a city but weighing more than our sun, can also emit X-rays if they're actively feeding. Some might be orphaned from their parent galaxies during collisions, left to drift alone while still siphoning gas from the cluster's sparse medium. Others could be part of hidden populations, neutron stars shrouded in dust or camouflaged against bright background light. But the plot thickens. A handful of these X-ray sources defy even these exotic explanations. Their energy signatures don't quite match known objects, sparking debates about whether we're seeing something entirely new. Could they be intermediate mass black holes, elusive middleweights between stellar and supermassive varieties? Or might some be linked to dark matter, annihilating or decaying in ways that emit X-rays? The latter is a long shot, but in a cluster as mysterious as Coma, even fringe ideas warrant a look. The implications are profound. If these sources are ejected black holes, they'd rewrite our understanding of how often galaxies kick out their central beast. If they're neutron stars, their sheer numbers could reveal how many stars meet violent ends in clusters. And if there's something stranger, well, that's the thrill of the Coma Cluster. It keeps us humble, reminding us that the universe always has another card up its sleeve. Up next, we'll unravel another puzzle, the eerie ring of galaxies looping through the cluster, a structure that might be a cosmic illusion or evidence of a collision for the ages. Now, let's turn our attention to one of the most visually striking oddities in the Coma Cluster, a ghostly ring of galaxies suspended in the cosmic void like a celestial crown. This vast structure, spanning millions of light-years, defies easy explanation. At first glance, it appears as if someone took a handful of galaxies and arranged them in a near-perfect loop, but the universe rarely does things just for show. So what's really going on here? One leading theory suggests this ring might be a cosmic mirage, a trick of perspective. Imagine holding a hula hoop and tilting it slightly away from you. From your viewpoint, it would look like an ellipse, even though it's still a perfect circle. Similarly, galaxies scattered in three-dimensional space along the rim of an enormous bubble could align just right from our vantage point on Earth, creating the illusion of a ring. Computer simulations show such projections can happen, especially in dense environments like the Coma Cluster where galaxies are packed tightly together. But there's a twist. Some researchers argue this ring isn't an illusion at all, but the echo of a colossal collision. Picture two smaller galaxy clusters smashing into the Coma Cluster billions of years ago. The gravitational shockwaves from such an impact could have sent ripples through the cluster's gas, compressing it into a spherical shell. Galaxies later forming in this compressed gas would inherit that shell-like arrangement, like foam riding the crest of a wave. Intriguingly, X-ray observations have spotted faint ripples in the cluster's hot gas, potential fingerprints of such a violent past, yet not everyone's convinced. Critics point out that the ring's galaxies don't all move in sync, as you'd expect if they were born from a single event. Some drift inward, others outward, suggesting they might just be passing through. Then there's the matter of scale. This ring is enormous, even by cosmic standards. Could a collision really create something so vast, or are we missing a piece of the puzzle? The debate gets even more fascinating when we zoom in on individual galaxies within the ring. Some show signs of recent star formation, as if they were jostled awake by the ring's formation. Others appear old and undisturbed, adding another layer of mystery. If the ring is a collision artifact, why do some galaxies seem unaffected? If it's a projection, why do so many show similar activity? What's clear is that this ring challenges our understanding of how structures evolve in the universe's most crowded neighborhoods. Whether it's a shadow play or a cosmic crash site, its existence forces us to rethink the rules. And that's the beauty of the Coma Cluster. It doesn't just hide its secrets, it dangles them in plain sight, daring us to look closer. Next up, we'll dive deeper into the collision scenarios that might have sculpted this enigmatic ring, exploring how gravity's invisible hand could shape something so extraordinary. Now, let's peel back another layer of this cosmic puzzle by examining the competing theories behind the ring's formation. One compelling idea is the slingshot effect, where a smaller galaxy cluster, think of it as a cosmic bullet, plunged through the heart of the Coma Cluster at breakneck speeds. As it passed, its gravity would have yanked on the surrounding galaxies, flinging some outward like stones from a catapult. Over time, these ejected galaxies could have settled into a ring-like pattern, their orbits sculpted by the gravitational aftershocks. Simulations of such high-speed encounters show that this chaotic dance can indeed produce ephemeral rings, though they typically dissolve within a few billion years. The fact that we still see this structure today raises questions. Was the collision more recent than we thought, or is some unseen force preserving it? Another twist comes from the concept of density waves. Picture dropping a pebble into a pond, the ripples spread outward, temporarily bunching up the water's surface. Similarly, a massive disturbance like a subcluster merger could send shock waves through the Coma Cluster's gas, creating regions where matter is compressed. Galaxies drifting into these high-density zones might slow down, piling up along the wave's edge like cars in a traffic jam. This could explain why some galaxies in the ring appear to be moving in unison while others seem oblivious. Supporters of this theory point to the faint X-ray ripples we mentioned earlier, potential echoes of the initial shock. But skeptics counter that the ring's sheer size stretches the limits of what a density wave could realistically achieve. Then there's the wild card, dark matter. Some models suggest the ring could be tracing the edges of a vast, invisible dark matter subhalo. Like an iceberg beneath the ocean's surface, its gravity might be herding galaxies into this peculiar arrangement without us seeing the culprit directly. If true, this would make the ring a rare, visible signature of dark matter's hidden architecture, a tantalizing clue for researchers. Yet, proving this is tricky, as dark matter's fingerprints are notoriously faint. What's striking is how each theory leaves gaps. The slingshot scenario struggles to explain the ring's longevity. Density waves can't easily account for its scale, and the dark matter angle remains speculative. This isn't just academic squabbling, it's a reminder of how much we still don't understand about the universe's most energetic events. The Coma Cluster's ring isn't just a curiosity, it's a laboratory for testing our ideas about gravity, collisions, and the invisible scaffolding of the cosmos. Up next, we'll tackle another head-scratcher: why the Coma Cluster seems to be missing dwarf galaxies, a discrepancy that could rewrite the rules of cosmic evolution. Now, shifting our gaze to another cosmic oddity, we encounter a puzzle that defies expectations: the curious scarcity of dwarf galaxies in the Coma Cluster. These small, faint galaxies should be everywhere, outnumbering their larger counterparts by a staggering margin, according to our current models of cosmic structure. Yet, when astronomers peer into the heart of the Coma Cluster, they find far fewer than predicted. Where did they all go? One leading explanation points to the brutal environment of the cluster itself. Imagine a school of fish swimming into a whirlpool. The smaller ones are the first to be torn apart. Similarly, dwarf galaxies, with their delicate gravitational grip, are especially vulnerable to the cluster's fierce tides. As they plunge through the Coma Cluster's dense core, the gravitational pull from massive galaxies and dark matter can stretch and shred them, scattering their stars into the intracluster void. This process, known as tidal disruption, might explain why so many dwarfs are missing. Supporting this, astronomers have spotted trails of stars, ghostly remnants of galaxies ripped apart, woven through the cluster like cosmic cobwebs. But could there be another culprit hiding in plain sight? Observational bias might also play a role. Dwarf galaxies are notoriously faint, and in a crowded, bright environment like the Coma Cluster, they could simply be lost in the glare. Think of trying to spot a firefly against a spotlight. Advanced telescopes and techniques are now uncovering more of these elusive objects, but the numbers still don't add up. Some researchers argue that even with better tools, the deficit remains real, suggesting destruction isn't the only factor at play. Then there's the dark matter angle. Many dwarf galaxies are thought to be anchored by hefty halos of dark matter, which should protect them from disintegration. If the missing dwarfs lacked these invisible shields, they'd dissolve quickly in the cluster's chaos. But why would some dwarfs have dark matter and others not? This ties back to larger mysteries about how dark matter is distributed, or whether our understanding of it needs revisiting. The implications stretch far beyond the Coma Cluster. Dwarf galaxies are cosmic fossils holding clues to the universe's early days. If they're being erased en masse, we might be losing vital pieces of the galactic origin story. Alternatively, their absence could hint at flaws in our models of galaxy formation, forcing us to rethink how structures evolve in the densest parts of the universe. This isn't just about counting galaxies, it's about uncovering the hidden rules governing cosmic survival. Up next, we'll explore an even stranger twist: elliptical galaxies in the Coma Cluster that defy expectations by sporting vibrant blue hues, a sign of stellar rebirth where none should exist. Now, let's turn our attention to a cosmic contradiction that's left astronomers scratching their heads: the unexpected presence of blue elliptical galaxies in the Coma Cluster. Normally, elliptical galaxies are the retirement homes of the universe, filled with old, red stars and little to no star formation. But these particular galaxies are breaking the rules, glowing with a youthful blue tint that suggests they're somehow producing new stars. How can galaxies that should be long dead suddenly spring back to life? One possibility is that these ellipticals aren't as dead as we thought. Imagine a dormant volcano that suddenly erupts. These galaxies might have been quietly holding onto reservoirs of cold gas, hidden deep within their cores. When disturbed, perhaps by a close encounter with another galaxy or a surge of gas from the surrounding cluster, that fuel could ignite a burst of star formation, painting the galaxy blue with hot, young stars. Observations have spotted faint traces of gas in some of these galaxies, lending weight to this idea. But in the Coma Cluster's harsh environment, where gas is stripped away by violent forces, how could these galaxies hold onto enough fuel to spark such a rebirth? Another theory points to galactic cannibalism. Elliptical galaxies often grow by merging with smaller neighbors. If one of these giants recently swallowed a gas-rich dwarf galaxy, the fresh supply of star-forming material could temporarily revive it. Think of it as a dying fire suddenly flaring up when you toss in a handful of dry kindling. astronomers have indeed found evidence of past mergers in some blue ellipticals, with distorted shapes or faint tidal tails hinting at a violent history. Yet not all blue ellipticals show these signs, leaving the puzzle unsolved. Then there's the role of the cluster itself. The Coma Cluster is a dynamic, chaotic place with galaxies whizzing past one another at incredible speeds. Could the sheer pressure of this environment squeeze gas within these galaxies, triggering star formation? It's a bit like shaking a soda can. Sometimes the disturbance forces things into action. Some simulations suggest this might happen, but the conditions would have to be just right, and not every elliptical in the cluster is affected. What makes this mystery even more intriguing is the timescale. Star formation is a fleeting phase in a galaxy's life, especially in a hostile place like the Coma Cluster. These blue ellipticals might be caught in a brief, almost rebellious moment of rejuvenation before fading back into red obscurity. That makes them cosmic oddities worth studying. They could teach us how galaxies cheat death, even if just for a little while. The implications stretch beyond the Coma Cluster. If dead galaxies can reignite, it challenges our understanding of galactic life cycles and the forces that govern them. Are we missing a piece of the puzzle, like an unknown energy source or a hidden process that replenishes gas? Or is the universe just full of surprises, ready to upend our expectations when we least expect it? Up next, we'll dive into another twist in the Coma Cluster's story: spiral galaxies that are losing their gas at an alarming rate, a phenomenon that could reveal even more about the cluster's unforgiving nature. Now, let's unravel another cosmic mystery that's as dramatic as it is destructive: the vanishing gas in spiral galaxies within the Coma Cluster. Picture a vibrant, star-forming spiral galaxy, its arms glittering with young, blue stars and vast clouds of gas, the raw material for new stellar births. But in the Coma Cluster, these galaxies are being stripped of their lifeblood, their gas reservoirs disappearing at an alarming rate. This isn't just a slow fade, it's a cosmic heist, and the culprit is the cluster's brutal environment. The main villain here is something called ram pressure stripping. Imagine a galaxy soaring through the cluster at incredibly high speeds, like a sprinter racing through a storm. The space between galaxies isn't empty, it's filled with a thin, superheated gas known as the intracluster medium. As a spiral galaxy plows through this searing onslaught, the pressure is so intense that it rips away the galaxy's own gas, like a strong wind tearing leaves from a tree. Over time, this leaves the galaxy gas poor, starving it of the material needed to form new stars. The result, a spiral galaxy that's slowly being transformed into a red and dead relic, its star-forming factories shutting down. But ram pressure stripping isn't the only force at work. The Coma Cluster's gravitational tides, the relentless pull from its enormous mass, also play a role. These tides can stretch and distort galaxies, loosening their grip on gas and making it easier for the intracluster medium to snatch it away. It's a one-two punch. The tides weaken the galaxy's defenses, and the ram pressure finishes the job. Astronomers have observed spiral galaxies in the cluster with tails of gas streaming behind them, like cosmic breadcrumbs marking the path of their destruction. These tails are telltale signs of the violent process underway. What makes this phenomenon even more fascinating is the speed at which it happens. In some cases, spiral galaxies can lose most of their gas in just a few 100 million years, a blink of an eye in cosmic terms. This rapid quenching explains why the Coma Cluster has so few star-forming spirals compared to quieter regions of the universe. The cluster isn't just a gathering of galaxies, it's a battlefield, and the spirals are on the losing side. Yet there's a twist. Not all spiral galaxies in the cluster succumb equally. Those on the outskirts, where the intracluster medium is less dense, might hold onto their gas longer. Others, if they're massive enough, can resist stripping thanks to their stronger gravity. It's a reminder that even in the harshest environments, survival strategies exist. Studying these holdouts could reveal clues about how galaxies adapt or fail to adapt to extreme conditions. The implications of this gas theft stretch far beyond the Coma Cluster. If RAM pressure stripping is this effective in dense environments, it could explain why galaxy clusters across the universe are dominated by red, lifeless galaxies. It's a universal process playing out wherever galaxies gather in large numbers. But here's the lingering question. Could some of this stripped gas linger in the cluster, eventually cooling and falling back onto galaxies, offering a fleeting chance for rebirth? Or is it lost forever, scattered into the vast nothing between galaxies? This phenomenon doesn't just highlight the violence of the cosmos, it also underscores how delicate the balance is between creation and destruction. Without gas, galaxies can't form stars, and without stars, they fade into obscurity. The Coma Cluster, in all its majesty, is also a graveyard for galactic potential. Up next, we'll explore another enigma: high-energy cosmic rays emanating from the cluster, whose origins are as mysterious as they are powerful. What could be generating these cosmic bullets, and what do they tell us about the hidden forces at work? Now, let's shift our gaze to another cosmic puzzle, one that's invisible to the naked eye, but packs an extraordinary punch. The Coma Cluster isn't just a realm of swirling galaxies and stolen gas. It's also a source of mysterious, high-energy cosmic rays, particles racing through space at nearly the speed of light. These aren't your everyday rays. They carry energy so immense that their origins baffle even the most seasoned astronomers. Where do they come from, and what cosmic accelerators could possibly launch them with such ferocity? Cosmic rays are like interstellar bullets, mostly made of protons and atomic nuclei, but some carry energies millions of times greater than anything we can produce in particle colliders on Earth. When they collide with other matter, they create cascades of secondary particles, leaving faint trails that detectors can pick up. But here's the catch: the ones streaming from the Coma Cluster don't quite fit the usual suspects. One leading theory points to active galactic nuclei, or AN, as the culprits. These are the supermassive black holes at the hearts of galaxies, devouring surrounding material and spewing out jets of plasma. These jets could act like natural particle accelerators, boosting cosmic rays to unimaginable energies. In the Coma Cluster, galaxies like NGC 4874 and NGC 4889 host such monstrous black holes, making them prime candidates. Yet, observations haven't definitively tied the rays to these AGN, leaving room for doubt. Then there's the explosive violence of supernova. When massive stars die in fiery blasts, their shockwaves can accelerate particles to extreme speeds. Over millennia, these remnants might contribute to the cosmic ray population. But here's the twist: the Coma Cluster's galaxies are largely red and dead, with little recent star formation. If supernova are to blame, where are all the young, massive stars needed to produce them? Now, let's venture into the realm of the speculative dark matter annihilation. Some theories suggest that when dark matter particles collide, they could annihilate each other, releasing bursts of energy and potentially high-energy cosmic rays. The Coma Cluster, dense with dark matter, seems like the perfect laboratory for this exotic process. But despite tantalizing hints, no smoking gun has been found. Detecting such signals is like listening for a whisper in a hurricane, given the background noise of other cosmic ray sources. What makes this mystery even more intriguing is the distribution of these rays. They're not concentrated around any single galaxy or structure, but seem to permeate the cluster diffusely. Could this suggest a collective origin, like the combined output of many weaker sources? Or is there something far more exotic at play, a yet undiscovered particle or phenomenon lurking in the cluster's depths? The implications stretch beyond the Coma Cluster. If we can pin down the source of these cosmic rays, it could shed light on the fundamental workings of particle acceleration in the universe. Are black holes the ultimate powerhouses? Is dark matter secretly fueling these particle barrages? Or is there an entirely new physics waiting to be uncovered? As we ponder these questions, the next enigma beckons a peculiar alignment of galaxies resembling a string of pearls. Is this a fleeting illusion of perspective, or a sign of the universe's hidden architecture? Let's unravel another cosmic curiosity, one that looks almost too perfect to be random. Stretching across the Coma Cluster is a striking lineup of galaxies, each gleaming like a bead on an invisible thread. Astronomers call it the string of pearls alignment, and it's either a breathtaking coincidence or a clue to the universe's hidden scaffolding. At first glance, this linear arrangement seems suspiciously orderly. Galaxies don't typically queue up in neat rows. They're more like guests at a crowded party, clustering in uneven groups. So when we spot a dozen or more galaxies strung along a near-perfect line, it begs the question, are we seeing a trick of perspective, or is there a deeper cosmic hand at work? One possibility is that it's just a fluke, a chance alignment of galaxies at different distances, like traffic lights lining up when viewed from the right angle. The universe is vast, and with enough galaxies, even unlikely patterns can emerge purely by accident. But the Coma Cluster's pearls are close enough to one another in space that this explanation feels shaky. Their shared motion and similar distances suggest they're truly connected, not just masquerading as a group. That leads us to the more tantalizing idea. This string might be a filament of the cosmic web. Picture the universe as a colossal spiderweb with galaxies clinging to its silken threads. These filaments, made mostly of dark matter and trace gas, stretch for millions of light years, funneling matter into dense clusters like the Coma. If the string of pearls marks one such filament, it's a rare snapshot of the universe's underlying architecture. Simulations support this. When scientists model the growth of cosmic structures, they see filaments threading through clusters with galaxies huddled along them like lights on a highway. But spotting these filaments in real life is tough. They're faint, and their gas is often too diffuse to detect. The Coma Cluster's pearl-like lineup might be one of the clearest examples we have. Yet mysteries remain. Why are these particular galaxies so evenly spaced? Some theories suggest they're relics of ancient collisions, where smaller galaxy groups merged and stretched into a line. Others propose that the dark matter filaments' gravity sculpted their positions over billions of years. Either way, their arrangement hints at forces beyond mere chance. The implications ripple outward. If this is a true filament, it could help explain how galaxies move and evolve within clusters. Filaments act as cosmic highways, channeling gas and galaxies into the cluster's heart. They might even fuel star formation by delivering fresh gas to hungry galaxies. But if it's not a filament, if it's something else entirely, then we're back to square one with a new puzzle to solve. As we marvel at this celestial necklace, another question tugs at the edges of our understanding, one about the cluster's most monstrous residents. Why do some black holes here defy the rules, growing far larger than their galaxies should allow? Now, let's turn our attention to a cosmic anomaly that defies expectations: the overmassive black holes lurking in the heart of the Coma Cluster's galaxies. These aren't your typical supermassive black holes. They're cosmic heavyweights, tipping the scales far beyond what their host galaxies should theoretically allow. Normally, galaxies and their central black holes grow in tandem, following what astronomers call the scaling relations. Picture it like a tree, and its roots, the bigger the tree, the larger the root system. But in the Coma Cluster, some black holes break this rule. They're like massive roots beneath a modest sapling, raising eyebrows and questions about how they got so disproportionately large. Take, for example, the black hole at the center of NGC 4889, one of the cluster's most massive galaxies. While NGC 4889 itself is enormous, its black hole is even more extreme, weighing in at around 20 billion times the mass of our Sun. That's several times heavier than predicted by standard scaling relations. How did this happen? One leading theory is that these black holes grew voraciously during the cluster's chaotic early history. Imagine a feeding frenzy where gas, stars, and even smaller black holes were funneled into the center during violent galaxy mergers. The Coma Cluster's dense environment would have made this easier, with galaxies colliding and merging more frequently than in quieter corners of the universe. But there's a twist. Some of these overmassive black holes aren't just relics of past feasting, they might also have grown through more exotic means. For instance, if a black hole formed from the direct collapse of a massive gas cloud in the early universe, it could have started out unusually large, skipping the typical gradual growth process. Alternatively, repeated mergers between black holes could have created these behemoths, especially if they occurred in rapid succession, leaving little time for the host galaxy to catch up in size. The implications are profound. If black holes can grow this large independent of their galaxies, it challenges our understanding of how these systems evolved together. It also raises questions about feedback, the way black holes inject energy into their surroundings, regulating star formation. An overmassive black hole might unleash more energy than its galaxy can handle, potentially shutting down star formation prematurely or even reshaping the galaxy's structure. Yet, mysteries persist. Why don't all galaxies in the Coma Cluster host such oversized black holes? Is there something special about the ones that do, like their location or merger history? And what does this mean for the broader cosmic population of black holes? These questions aren't just academic, they could reshape our models of galaxy formation and the role black holes play in it. As we grapple with these cosmic oddities, another puzzle emerges, one about the faint, ghostly radio signals whispering through the cluster. What secrets do these elusive waves hold? Now, let's shift our gaze to the whispers of the cosmos, those faint, diffuse radio sources drifting through the Coma Cluster like ghostly echoes. Unlike the powerful bursts from active galactic nuclei or the bright emissions of star-forming regions, these signals are subtle, almost elusive, leaving astronomers scratching their heads. What could be producing these quiet yet persistent radio waves in the heart of this crowded cluster? One leading explanation points to the remnants of past activity from active galactic nuclei. Picture a supermassive black hole that once feasted on surrounding gas, launching jets of high-energy particles into space. Over time, that frenzy faded, leaving behind a faint afterglow like embers cooling after a fire. These remnants, known as radio ghosts, could be the fading signatures of jets that powered down millions or even billions of years ago. The Coma Cluster's dense environment might preserve these signals longer than in isolated galaxies, acting like a cosmic freezer that slows their dissipation. But not all of these faint radio sources fit neatly into this category. Some appear too spread out or lack the telltale structure of old Aegean jets. This has led researchers to consider more exotic possibilities. For instance, could they be traces of turbulent magnetic fields, amplified by the cluster's violent merger history? When galaxies collide or gas sloshes around during cluster formation, it could stir up magnetic energy, creating diffuse radio halos or filaments. The Coma Cluster's notorious turbulence makes it a prime candidate for such phenomena. Another intriguing idea involves cosmic rays, high-energy particles zipping through space. If these particles interact with the cluster's magnetic fields, they could produce the faint radio glow we detect. But here's the twist: the exact source of these cosmic rays remains unclear. Are they accelerated by ancient supernova explosions, or could they be tied to unseen dark matter annihilation? The latter possibility, though speculative, opens a door to one of astrophysics' biggest mysteries. Then there's the question of distribution. These faint radio sources aren't scattered randomly. They often cluster near regions where galaxies have recently interacted. This hints that their origins might be tied to the dynamic, messy processes of galaxy evolution. For example, when galaxies pass close to one another, their gravitational tug of war can strip gas and inject energy into the surrounding medium, sparking low-level radio emissions. It's like ripples in a pond after a stone's throw, but on a cosmic scale. The challenge in studying these signals lies in their faintness. Cutting-edge telescopes like the Low-Frequency Array LOFAR and the upcoming Square Kilometre Array are pushing the boundaries, teasing out details that were once invisible. Each new observation brings us closer to understanding whether these whispers are cosmic relics, byproducts of turbulence, or something entirely unexpected. As we piece together the puzzle of these faint radio murmurs, another enigma demands our attention, one that revolves around the cluster's so-called red and dead galaxies, where star formation has mysteriously ceased. What forces could have silenced these cosmic giants so completely? Now, turning our attention from the faint whispers of radio emissions, we encounter a stark cosmic contrast, the eerie silence of the so-called red and dead galaxies. These aging giants scattered throughout the Coma Cluster glow with a dull reddish hue, a telltale sign that their star-forming days ended long ago. Unlike their vibrant blue star-birthing counterparts, these galaxies are cosmic graveyards where stellar nurseries have shut down entirely. But the question is, why here? Why does the Coma Cluster host such an overwhelming number of these quenched galaxies, and what forces conspired to snuff out their star formation so effectively? One of the primary culprits is the cluster's densely packed environment. The Coma Cluster is a crowded, chaotic place with galaxies whizzing past one another at incredible speeds. When a gas-rich spiral galaxy ventures too close to the cluster's core, it faces a brutal onslaught. The immense gravitational pull of the cluster itself, combined with the searing heat of the hot intergalactic gas, strips away the galaxy's fuel reserves in a process called ram pressure stripping. Picture a gust of wind ripping leaves from a tree, only here, the wind is a torrent of million-degree plasma, and the leaves are the cold gas clouds needed to form new stars. Without this vital fuel, the galaxy's star formation grinds to a halt, leaving it to fade into a red, lifeless state. But ram pressure stripping isn't the only villain in this cosmic tale. Another key player is galaxy harassment, a dramatic term for the cumulative gravitational jostling that occurs when galaxies repeatedly pass near one another. These close encounters can distort a galaxy's shape, funneling its gas into the central supermassive black hole or flinging it out into space. Over time, this relentless battering leaves the galaxy gas poor and unable to birth new stars. Think of it like a busy marketplace where everyone is bumping into each other. Eventually, you'll drop what you're carrying. In the Coma Cluster, these interactions happen on a grand scale with devastating efficiency. Then there's the role of the cluster's ancient history. The Coma Cluster is one of the most massive and evolved structures in the universe, meaning many of its galaxies have had billions of years to exhaust their gas supplies. Unlike younger clusters where star formation might still flicker in some galaxies, Coma's dense environment has had ample time to quench its members. Some researchers argue that the cluster's early formation allowed it to develop a particularly harsh environment, where conditions for star death far outweighed those for star birth. In essence, Coma became a galactic retirement home far earlier than most clusters, leaving its galaxies to slowly redden and fade. Yet, even among these red and dead galaxies, there are puzzling exceptions. A small number show signs of lingering star formation or odd structural features, as if they're clinging to the last vestiges of youth. These outliers suggest that quenching isn't always a one-size-fits-all process. Some galaxies might resist having their gas stripped away, perhaps due to their angle of entry into the cluster or an unusually robust supply of fuel. Others might experience brief bursts of star formation when they collide with stray gas clouds, like a dying flame flaring up one last time before going out. Understanding these red and dead galaxies isn't just about solving a cosmic mystery, it's about piecing together the life cycle of galaxies themselves. The Coma Cluster acts as a time capsule, showing us what happens to galaxies when they're subjected to extreme conditions over billions of years. And as we study them, we're forced to confront a deeper truth. The universe is an ever-changing place where even the mightiest galaxies can't escape the slow march of time. With this in mind, let's pivot to another cosmic oddity, the strangely distorted shapes of some Coma Cluster galaxies, where gravity and pressure have twisted them into bizarre, almost artistic forms. Now, shifting our gaze to the cosmic oddities of shape and structure, we encounter some of the most visually striking inhabitants of the Coma Cluster galaxies, twisted into forms so bizarre they defy the usual classifications. These aren't your typical spirals or smooth ellipticals. Instead, they resemble cosmic accidents sculpted by the relentless forces of their environment. Among them, jellyfish galaxies stand out, their delicate tendrils of gas streaming behind them like ethereal tails, as if caught in some invisible current. And then there are the distorted spirals, their once orderly arms stretched and warped into chaotic swirls, like a painting smudged by an unseen hand. But what's behind these peculiar shapes? The answer lies in the Coma Cluster's extreme and unforgiving nature. Take the jellyfish galaxies, for instance. Their trailing gas filaments aren't the result of some internal process, they're the aftermath of a galactic ordeal. As these galaxies plunge through the cluster at high speeds, they collide with the superheated gas filling the space between galaxies. This intergalactic medium acts like a cosmic wind, violently stripping away their cooler gas reserves. But instead of disappearing entirely, the gas is wrenched into long, luminous trails, lit up by the very forces tearing it apart. Imagine running through a downpour with a banner. The fabric would stream behind you, whipped by the wind. That's precisely what's happening here, only on a scale so vast. The banner is the galaxy's own star-forming material, and the rain is a storm of high-energy particles. These jellyfish galaxies aren't just curiosities, they're cosmic snapshots of a galaxy in the midst of losing its vitality, a stark reminder of how dynamic and destructive the universe can be. Then there are the distorted spirals, their elegant symmetry shattered by the cluster's gravitational chaos. Unlike isolated spiral galaxies, which can maintain their pinwheel structure for billions of years, spirals in the Coma Cluster face constant gravitational harassment. As they weave through the crowded cluster, the combined gravitational pull of neighboring galaxies tugs at their stars and gas, twisting their shapes into something unrecognizable. Some appear almost shredded, their arms pulled into long, faint streams, while others are warped into lopsided, asymmetrical forms. It's as if the cluster itself is a sculptor, and its tools are gravity and motion, endlessly reshaping anything that lingers too long in its grasp. But perhaps the most intriguing aspect of these odd morphologies is what they reveal about the cluster's history. The sheer variety of distorted shapes suggests that the Coma Cluster isn't just a monolithic entity. It's a patchwork of different interactions, collisions, and near misses, each leaving its mark on the galaxies caught in the turmoil. Some galaxies might show signs of recent encounters, their shapes still fresh with disruption, while others bear the scars of ancient run-ins, their structures permanently altered. And then there are those caught in the act, like the jellyfish galaxies, offering astronomers a rare chance to study these processes in real time. What makes these peculiar galaxies especially valuable is that they serve as cosmic diagnostics. By studying their shapes, scientists can infer the properties of the cluster's invisible components, like the distribution of dark matter or the turbulence of the intracluster gas. A galaxy's distortion can act like a fingerprint, revealing the forces that acted upon it. For example, the angle and length of a jellyfish galaxy's gas tail can tell us about the speed and direction of its movement, while the degree of warping in a spiral can hint at the strength of past gravitational encounters. These galaxies aren't just oddities, they're messengers carrying clues about the cluster's hidden dynamics. Yet, even as we decode these shapes, mysteries remain. Why do some galaxies become jellyfish-like while others simply fade into red, lifeless disks? How much of a role does a galaxy's initial mass or gas content play in determining its fate? And could some of these distorted structures hint at even stranger phenomena, like interactions with unseen dark matter clumps? The Coma Cluster's gallery of peculiar galaxies is far from fully understood, and each discovery peels back another layer of this cosmic puzzle. As we move forward, let's turn our attention to another enigma, the puzzling absence of expected matter in the cluster, where visible baryons seem to vanish without a trace. Now, turning our attention to one of the most persistent puzzles in modern astrophysics, we arrive at the enigma of the missing baryons. These are the building blocks of ordinary matter, protons, neutrons, and electrons, that make up everything we see, from stars to galaxies to our own bodies. But here's the catch: when astronomers tally up all the visible matter in the Coma Cluster, the numbers don't add up. A significant portion of these baryons seems to have vanished into thin space, defying our best predictions. The question is, where did they go? The leading suspect in this cosmic whodunit is the warm-hot intergalactic medium, often abbreviated as WIM. This elusive material is thought to exist in the vast spaces between galaxies, a diffuse web of gas that's been heated to temperatures of hundreds of thousands or even millions of degrees. Unlike the cooler gas inside galaxies, which glows brightly in optical or radio light, the WIM is so hot and thin that it's nearly invisible to traditional telescopes. It emits faint X-rays, but even those signals are easily drowned out by the brighter emissions from galaxies and galaxy clusters. So how do we know the WIM exists at all? The clues come from clever detective work. When light from distant quasars passes through the cosmic web on its way to Earth, astronomers can analyze its spectrum for subtle absorption lines, tiny dips in brightness that correspond to specific elements in the WIM. These fingerprints reveal the presence of ionized oxygen and other heavy elements, confirming that the WIM isn't just empty space. But here's the frustrating part. Even when we account for all these detections, the total amount of baryons still falls short of what theory suggests should be there. The Coma Cluster, with its extreme density and activity, should be brimming with these particles, yet they remain stubbornly hidden. One possibility is that the missing baryons are lurking in an even more elusive form, perhaps as ultra-diffuse gas clouds that are too faint to detect with current technology. Another theory suggests that some of this matter might have been ejected from galaxies during violent events like supernova or black hole outbursts, scattering it so far and wide that it's effectively invisible. There's even speculation that a fraction of these baryons could have been converted into exotic particles, though that remains highly controversial. What makes the mystery even more intriguing is that the missing baryon problem isn't unique to the Coma Cluster. It's a cosmic-scale issue. Observations of the entire universe suggest that roughly half of all baryons are unaccounted for, meaning this isn't just a local anomaly but a fundamental gap in our understanding of how matter is distributed. Solving this puzzle could reshape our models of galaxy formation, cluster evolution, and even the large-scale structure of the cosmos. As we push the boundaries of detection with next-generation X-ray telescopes and advanced spectroscopic techniques, the hope is that the WIM will finally give up its secrets. Until then, the missing baryons remain one of the most tantalizing unsolved problems in astrophysics, a reminder that even the most familiar ingredients of the universe can still surprise us. Next, we'll dive deeper into the cutting-edge methods scientists are using to hunt for these elusive particles, probing the faintest signals in the hope of closing this cosmic case. Now, let's take a closer look at the high-stakes hunt for the warm-hot intergalactic medium, the cosmic detective work that could finally solve the missing baryon mystery. Scientists aren't just sitting back and waiting for answers. they're deploying some of the most advanced tools in astrophysics to track down this elusive material, pushing the limits of technology and ingenuity. One of the key strategies in this search involves X-ray telescopes, specifically designed to detect the faint glow of million-degree gas. Instruments like the Chandra X-ray Observatory and XMM Newton have been pivotal, scanning the skies for subtle emissions that might reveal the WIM hiding spots. But here's the challenge. The signal is incredibly weak, often drowned out by brighter sources like active galaxies or even the diffuse X-ray background of the universe itself. It's like trying to spot a single candle flickering in a stadium flooded with spotlights. To overcome this, astronomers have turned to a clever workaround, stacking observations. By combining data from multiple sightlines, areas where the cosmic web is predicted to be densest, they can amplify the WIM faint signal, teasing it out from the noise. This method has yielded tantalizing hints, including detections of ionized oxygen and other heavy elements in the spaces between galaxies. But these findings are still provisional, like catching a whisper in a crowded room. Another promising approach leverages the absorption of light from distant quasars, those brilliant beacons powered by supermassive black holes. As quasar light travels through the cosmic web, it passes through filaments of the WIM, leaving behind telltale absorption lines in its spectrum. Missions like the Hubble Space Telescope and the upcoming European Space Agency's Athena mission are fine-tuning this technique, aiming to map the WIM distribution with unprecedented precision. Yet even here, obstacles remain. The WIM-diffused nature means these absorption features are often incredibly faint, requiring hours, sometimes days of observation to confirm. Perhaps the most ambitious effort yet is the use of fast radio bursts, or FRB. These mysterious, millisecond-long flashes of radio waves originate from distant galaxies, and as they travel through the universe, their signals are subtly altered by the WIM. By analyzing how these bursts are dispersed, scientists can estimate the density of electrons, and by extension, baryons along their path. It's a groundbreaking method, but FRBs are notoriously unpredictable, making them a tricky tool to rely on. The Coma Cluster, with its dense environment and complex dynamics, presents a unique testing ground for these techniques. Its sheer size and gravitational pull should concentrate the WIM, making it slightly easier to detect. But even here, the results have been mixed. Some studies claim tentative detections, while others come up empty-handed, highlighting just how elusive this material truly is. What makes the search even harder is the WIM-patchy, uneven distribution. Unlike the smooth gas clouds we're used to, the WIM is thought to exist in a tangled, thread-like structure, following the invisible scaffolding of the cosmic web. This means it's not uniformly spread out but clumped in filaments and knots, requiring astronomers to scan vast swaths of sky to piece together a complete picture. Despite these hurdles, the stakes couldn't be higher. Finding the WIM wouldn't just solve the missing baryon problem, it would revolutionize our understanding of how matter flows through the universe, how galaxies form, and even how the cosmic web itself evolved. Next-generation telescopes like the Lynx X-ray Observatory and the Square Kilometre Array promise to bring us closer than ever to cracking this case. Until then, the hunt continues, a testament to human curiosity and the enduring allure of the universe's greatest mysteries. Up next, we'll explore another baffling phenomenon in the Coma Cluster, one that might hold unexpected clues to the WIM whereabouts. Now, shifting our gaze to another electrifying mystery, let's explore a phenomenon as fleeting as it is powerful: fast radio bursts. These enigmatic cosmic flashes last mere milliseconds, yet they pack more energy than the sun emits in days. Could the turbulent, high-energy environment of the Coma Cluster be a breeding ground for these mysterious signals? The possibility has scientists buzzing with intrigue. Fast radio bursts, or FRB, were first discovered in 2007, and their origins remain one of astronomy's most tantalizing puzzles. Some erupt just once, while others repeat sporadically, adding layers to their mystery. The leading theories range from magnetars, highly magnetized neutron stars, to collisions between dense objects like black holes or neutron stars, but the Coma Cluster's unique conditions open up another compelling angle. With its dense galaxy population, raging magnetic fields, and violent gravitational interactions, this cluster might just be the perfect incubator for FRBs. One tantalizing clue lies in the cluster's abundance of magnetars. These stellar remnants, born from supernova explosions, possess magnetic fields trillions of times stronger than Earth. When they glitch or undergo sudden crustal fractures, they can release colossal bursts of energy, potentially manifesting as FRBs. The Coma Cluster's rich stellar environment, with its frequent supernova and stellar collisions, could host a higher than usual number of these explosive objects. Then there's the role of the cluster's intracluster medium, the hot, magnetized gas filling the space between galaxies. As FRBs travel through this turbulent sea, their signals could be scattered or distorted, offering astronomers a unique way to probe the cluster's invisible magnetic fields and plasma density. A few tentative FRB detections have been tentatively linked to galaxy clusters, though none yet definitively tied to Coma. Still, the mere possibility has researchers reanalyzing old data and scanning the skies for new bursts. Interestingly, FRBs might also hold the key to solving the missing baryon problem we discussed earlier. Their dispersion, how their signal stretches as it travels through intergalactic space, can reveal the density of electrons along their path, effectively mapping the warm, hot intergalactic medium. If an FRB were detected within or behind the Coma Cluster, it could provide unprecedented insights into both phenomena at once. But pinning down FRBs in Coma is no easy feat. Their unpredictability means astronomers rely on luck and patience, with radio telescopes like CHIME and ASCAP scanning vast swaths of sky around the clock. Even then, pinpointing a burst's exact origin within a dense cluster like Coma requires ultra-precise follow-up observations, a challenge given FRB's fleeting nature. Despite these hurdles, the potential rewards are immense. Confirming an FRB's connection to the Coma Cluster would not only shed light on the burst's origin, but also illuminate the cluster's most chaotic corners. It could reveal hidden magnetars, unmapped magnetic fields, or even entirely new astrophysical processes. For now, the question remains open, a thrilling reminder of how much we have yet to uncover. As we venture deeper into the Coma Cluster's enigmas, our next stop takes us to an even more elusive quarry, dark matter clumps that defy explanation, lurking where no galaxies dare to shine. But before we unravel the secrets of those invisible clumps, let's consider this. What if dark matter isn't just a smooth, uniform veil draped across the cosmos, but instead it's lumpy, gathering in hidden pockets where no stars shine? This brings us to one of the Coma Cluster's most perplexing riddles: dark matter clumps that defy expectations. Gravitational lensing, nature's own cosmic magnifying glass, has given us our best glimpses of these elusive structures. When light from distant galaxies passes through the Coma Cluster, its path bends around the cluster's immense gravity, distorting the images we see. By mapping these distortions, astronomers can trace the cluster's mass distribution, including the dark matter we can't directly observe. Surprisingly, these studies have revealed dense knots of dark matter, termed subhalos, floating untethered to any visible galaxy. It's as if the universe left behind invisible footprints, hinting at a history we're only beginning to decipher. The existence of these isolated subhalos poses a major challenge to our understanding of dark matter. According to leading theories like cold dark matter models, these clumps should act as scaffolding for galaxies to form. So why are some of them drifting alone, devoid of stars? One possibility is that they once hosted galaxies, but the brutal environment of the Coma Cluster, with its gravitational tides and galaxy collisions, stripped them away, leaving behind naked dark matter. Another twist, these subhalos might be failed galaxies, pockets where gas never cooled enough to ignite star formation. Yet gravitational lensing isn't a perfect tool. Its resolution is limited, making it difficult to detect the smallest subhalos, and the observations can be muddled by the cluster's complex structure. Some claim detections might even be artifacts of the lensing models themselves. To complicate things further, alternative theories like self-interacting dark matter predict smoother mass distributions, clashing with the clumpy signatures we observe. The hunt for answers is driving innovative techniques. Astronomers are now combining lensing data with simulations of the cluster's evolution, hoping to reconstruct how these subhalos came to be. Meanwhile, upcoming telescopes like the Vera Rubin Observatory promise sharper views, potentially revealing fainter, smaller clumps. If these dark matter pockets are confirmed, they could rewrite the rules of galaxy formation and even help us pinpoint what dark matter truly is. Are they cosmic ghosts, relics of a violent past, or something even stranger? For now, they remain silent, shadowy puzzles in the Coma Cluster's grand tapestry. And speaking of cosmic shadows, our final stop takes us to an unexpected spark of light regions where star formation defies all odds, flourishing against the cluster's harsh backdrop. But even in the cosmic desert of the Coma Cluster, where gas is scarce and gravitational forces are relentless, there are surprising oases, pockets where new stars are being born against all odds. These unexpected nurseries challenge everything we thought we knew about how galaxies evolve in one of the most extreme environments in the universe. Picture this: most galaxies in dense clusters like Coma are red and dead, their gas stripped away by violent interactions or heated to extremes, leaving them unable to form new stars. Yet, scattered among these aging galaxies, astronomers have spotted rare patches of blue telltale signs of fresh, young stars. How are these stellar newborns surviving in a place that should have snuffed them out long ago? One leading theory points to stealthy reservoirs of cold gas. While the Coma Cluster's hot, X-ray emitting gas dominates, some galaxies may still harbor hidden pockets of cooler, denser material. These could be leftovers from their pre-cluster days, shielded from destruction by their own gravity or tucked away in galactic cores. When this cold gas collapses under its own weight, it ignites star formation, creating brief but brilliant bursts of youth in an otherwise aging population. Another possibility is galactic mergers. Even in the high-speed chaos of the cluster, two gas-rich galaxies might occasionally collide, funneling material into their centers and triggering starbursts. These events would be fleeting, perhaps just tens of millions of years, but they'd leave behind a clear signature: clusters of massive, hot stars that stand out against their redder neighbors. Then there's the wild card: cosmic recycling. As older stars die, they expel enriched gas back into their host galaxies. In some cases, this recycled material might cool and reignite star formation, like a phoenix rising from the ashes. It's a delicate balance, though. Too much turbulence from the surrounding cluster, and the gas gets blown away before it can settle. Observing these star-forming oases isn't easy. Their signals are faint, often drowned out by the glare of nearby giants. But advanced telescopes like the Hubble and the upcoming James Webb Space Telescope are peeling back the layers, revealing the delicate dance of gas and gravity that keeps these stellar nurseries alive. The implications are profound. If star formation can persist here, in one of the harshest environments imaginable, it forces us to rethink how galaxies adapt or resist the pressures of cluster life. Are these oases the last gasps of dying galaxies, or proof that the universe always finds a way to create, even in the most unlikely places? And as we ponder that question, another mystery emerges, one that defies even the laws of gravity itself. Our next stop, a supermassive black hole that seems to have gone rogue, hurtling through the cluster without a home. Now, shifting our gaze to one of the most dramatic cosmic fugitives in the Coma Cluster, we come across a supermassive black hole that appears to have broken free from its galactic home. Imagine a behemoth millions or even billions of times the mass of our Sun, hurling through space without a galaxy to anchor it. This isn't science fiction, it's a real possibility astronomers are grappling with. What could rip a supermassive black hole from the heart of its galaxy? The leading suspect is a galactic collision. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance. But if a third galaxy joins the fray, the chaotic interplay of forces can fling one of the black holes outward at incredible speeds. Think of it like a slingshot effect, except on a scale so vast it defies intuition. The evidence for this runaway black hole is indirect but compelling. Telescopes have spotted a streak of superheated gas trailing behind what could be the black hole, like a cosmic wake. As the black hole plows through the cluster's intergalactic medium, it shocks the surrounding gas, making it glow in X-rays. This eerie trail, stretching thousands of light years, hints at something massive and fast-moving disturbing the fabric of space. Gravitational waves might hold another clue. When black holes merge, they send ripples through space-time like tossing a stone into a pond. If the merger is lopsided, the recoil could kick the newly formed black hole away at speeds high enough to escape its galaxy's grip. While we haven't detected gravitational waves from this specific event, future observatories like LISA, the Laser Interferometer Space Antenna, could catch similar cosmic recoils in action. But there's a twist. Some researchers argue this X-ray streak might not be a black hole at all, but rather a jet from an active galactic nucleus pointing straight at us. Or it could be a filament of gas unrelated to any rogue object. The debate highlights how tricky it is to interpret these distant signals, especially when dealing with phenomena that push the limits of our understanding. If confirmed, a runaway supermassive black hole would rewrite the rules of galactic evolution. It would prove that even the most anchored objects in the universe can be uprooted, sent careening through the void. What happens to a galaxy stripped of its central black hole? Does it wither, or does it find a new equilibrium? The answers could reshape our theories about how clusters like Coma evolve over billions of years. As we ponder the fate of this cosmic fugitive, another mystery calls one tied to the very fabric of the universe itself. Next, we'll explore how the Coma Cluster's puzzles might be linked to the vast cosmic web, the scaffolding that connects all things in the cosmos. But the mysteries of the Coma Cluster don't exist in isolation. They're threads woven into a much grander cosmic tapestry. To truly understand this region of space, we need to zoom out and see how it fits into the sprawling architecture of the universe itself. Enter the cosmic web, the vast network of thin filaments and immense voids that structure everything we see on the largest scales. Picture the universe not as a random scattering of galaxies, but as an intricate spiderweb. The threads of this web, filaments made of dark matter and gas, stretch across billions of light years, connecting clusters like beads on a string. The Coma Cluster sits at one of these dense intersections where multiple filaments converge, funneling matter and energy into its core. Meanwhile, the voids, those enormous, nearly empty regions between filaments, act like cosmic deserts, shaping how clusters grow and evolve. Simulations of the cosmic web reveal something astonishing. The Coma Cluster's quirks might be fingerprints of this larger structure. Take its missing dwarf galaxies, for example. While we'd expect thousands of these faint satellites, they're strangely sparse. One theory suggests the cosmic web's tidal forces, those same invisible threads guiding galaxies, could be tearing dwarf galaxies apart or flinging them into the voids where they're lost to observation. Then there's the hot gas overabundance. The cluster's X-ray glow is far brighter than predicted, hinting at hidden reservoirs of energy. Simulations show that when filaments channel gas into clusters at high speeds, shock waves ripple through the intracluster medium, heating it to extreme temperatures. These cosmic highways might be pumping the Coma Cluster full of extra energy, solving one mystery while deepening our awe of the web's influence. Even the peculiar alignment of galaxies, like the string of pearls we explored earlier, finds an explanation here. The cosmic web doesn't just guide matter, it spins galaxies into alignment along its filaments. As galaxies fall into the cluster, they often follow these invisible tracks, lining up like cars on a freeway. What seems like a random arrangement might actually be a snapshot of the web's gravitational choreography. But the cosmic web isn't just a passive scaffold, it's dynamic. As dark matter and gas flow along filaments, they trigger bursts of star formation, fuel supermassive black holes, and even dictate how clusters collide. The Coma Cluster's violent mergers, its runaway black holes, even its ghostly radio halo, all could be echoes of the web's eternal reshaping. Yet for all its power, the cosmic web remains elusive. We can map its broad strokes through galaxy surveys, but its finest threads are too faint to see directly. Future telescopes, like the European Space Agency's Euclid, aim to trace the web in 3D by observing how its gravity distorts the light of distant galaxies. With every new map, we get closer to understanding how this hidden framework molds everything from galaxy clusters to individual stars. So what does this mean for the Coma Cluster? It's not just a collection of oddities, it's a window into the forces that built the universe. Each mystery, from the missing dark matter to the rogue black holes, reflects the cosmic web's invisible hand at work. And as we unravel one thread, we pull on the entire tapestry, revealing connections far beyond what we once imagined possible. With that, we've reached the end of our journey through the Coma Cluster's greatest enigmas. But the universe never stops surprising us, so stay curious, keep looking up, and who knows what mysteries we'll uncover next. If you enjoyed this cosmic deep dive, don't forget to like, subscribe, and hit that notification bell so you won't miss our next adventure into the unknown. Until then, keep wondering. As we reflect on the 25 unexplained phenomena within the Coma Cluster, one thing becomes undeniably clear. This region of space is not just a collection of cosmic oddities. It's a living laboratory, challenging everything we thought we knew about the universe. From galaxies that defy the laws of gravity to black holes that vanish without a trace, each mystery peels back another layer of our cosmic ignorance, revealing just how much we still have to learn. Take the missing dark matter, for example. Its absence in certain galaxies forces us to rethink our models of how matter behaves on the largest scales. Then there's the eerie ultra-diffuse galaxies, drifting like ghosts through the cluster, their survival a puzzle that rewrites the rules of galactic evolution. And who could forget the colossal radio halo, a silent hum of energy with no clear source, whispering secrets about magnetic fields and particle physics we're only beginning to grasp. But the Coma Cluster isn't just about posing questions, it's also a teacher. The violent mergers, the rogue black holes, the galaxies stripped of their gas, they all paint a picture of a dynamic, ever-changing universe where chaos and order dance in an intricate balance. These phenomena don't just baffle us, they refine our theories, pushing astronomers to develop sharper tools and bolder ideas. Even the cosmic web, with its invisible threads weaving through space, shows us how interconnected everything truly is. What's remarkable is how these mysteries span such a vast range of scales. From the tiniest flickers of X-rays to the grand alignment of galaxies along filaments, the Coma Cluster is a reminder that the universe operates on levels we're still struggling to comprehend. And with each discovery, whether it's a faint radio signal or an unexpected burst of star formation, we're not just solving puzzles, we're rewriting the story of the cosmos itself. So what's next? The beauty of astronomy is that the more we learn, the more questions arise. Future telescopes like the James Webb Space Telescope and the upcoming Square Kilometre Array will peer deeper into the Coma Cluster's secrets, uncovering clues we can't yet imagine. Perhaps we'll finally detect the missing baryons hiding in the warm, hot intergalactic medium. or catch a fast radio burst in the act, revealing its elusive origins. But here's the real magic. You don't need a telescope to be part of this journey. Every time you look up at the night sky, you're joining a tradition of curiosity that stretches back millennia. The Coma Cluster's mysteries belong to all of us, a shared challenge that unites scientists and stargazers alike. So keep wondering, keep questioning, and most importantly, keep exploring. If this cosmic adventure has sparked your curiosity, don't let it end here. Hit that subscribe button so you won't miss our next dive into the universe's greatest enigmas. Share your thoughts in the comments. Which of these 25 phenomena fascinates you the most? And as always, stay tuned, because the cosmos has a way of surprising us when we least expect it. The universe is vast, mysterious, and endlessly generous with its secrets, so let's keep searching together.